Okay, maybe we could get started. It's my pleasure to introduce Mauro Morales, who's a PhD student here at University of Technology Sydney, the Centre for Quantum Software and Information. He's going to be talking about some research he completed earlier this year on Fermion sampling with a number of his collaborators. Take it away, Mauro.
Thank you. So yeah, this work I'm going to present is what I've been doing with my collaborators, with Michal Oshmaniek and Nina Daniam in the Center for Theoretical Physics in the Polish Academy of Sciences, and with Zoltán Zimborás at the Wigner Research Institute for Physics in Hungary. So this work is in the archive if you want to see it. We'll probably update it very soon. And the work is titled Fermion Sampling. So as you can guess, it's some kind of analog of boson sampling. So first, let's start with the motivation for these sampling schemes. So I think we all know what quantum supremacy is, the idea of performing this computational task on a quantum computer, that it's not feasible for classical ones. Of course, this definition is a bit vague, but it's what motivates this research. And then we know that the current quantum computers are quite noisy, very small, small in number of qubits. The depths of the unitaries we can apply are not very large. So this constrains what we can run on the quantum computers. And then we would like to run some quantum algorithms in these computers, but the problem is that we would like some theoretical guarantees that there's actually some advantage with respect with the classical machines. So we could think of two options here. One, of course, is, okay, we run, for example, Shor's algorithm. So one could say there's some theoretical guarantee that there are advantages. So factorizing is hard. But the problem is that the number of qubits we require and the depths are too big. So this is not feasible with current machines. A second option would be, okay, maybe we can run some variational algorithm, maybe solve some chemistry problem or some optimization problem. So here is VQE, for example. But the problem is that arguably there's not as a strong theoretical guarantee that we are actually having some advantage. So this is what motivates these sampling problems, like the one that Google performed some time ago. So in practice, kind of fulfills these two requirements of complexity theoretical guarantees that this is not feasible, or at least evidence for it, and that it's implementable with the near-term hardware. So Google did experiment with 53 qubits in its Sycamore processor, and by running random circuits on their device, they managed to sample, they literally sample bit strings from the device, and they show that it's unlikely that classical computers can sample from similar probability distributions as the ones generated by this quantum computer. So, okay, so this kind of scheme is called random circuit sampling. There's also, one could call, simplified versions of it. So you take some, what sometimes is called an architecture. So you take some random 2-qubit gates, and then you generate this random unitary. You sample from it. There's also, of course, boson sampling, as you may know, and it's near causing the Gaussian boson sampling. So this was implemented a while ago in China. They used 100 modes and 50 photons, if I recall correctly, claiming that they achieved this quantum supremacy or quantum advantage. So last year, when I started learning on all these things, and I was learning about boson sampling, I thought to myself, okay, but what about fermions? Can I have like a fermion sampling? Does it even make sense? Is it interesting? Well, it turns out there's been some work on that actually. So here I'm showing a work from the last year where they study this. Here the title is computational power of match gates. So these match gates are actually related to free fermions. And when they're supplemented with some resources, it turns out that you can actually get these results of hardness of sampling. Now, when this work came out, and there were also other previous works, let's say that the theoretical results that were available were not at the same level of random circuit sampling or boson sampling. So there are some conjectures involved in these results, which were not clear that were true in the fermion case. So what I'm going to show you today is how we prove some of these results. Not all of them, but some of them. So so as I explained before, these sampling problems in general is, I have some random set of unitaries that I choose randomly, then once chosen, I sample from it and I get some probability distribution. Now there are two notions of approximation that I will be using in this presentation. So we say that Q approximates relatively P, the probability distribution P, if this is true. So the error depends on P as well. There's some fraction of P, and then there's a notion of additive approximation. And then in all these sampling problems, what essentially everything boils down to is that we have some classical machine that is able to sample from a distribution that additively approximates the output probabilities of this U. And this plus some conjectures implies something that is thought to be unlikely, which is that the polynomial hierarchy collapses. So this is what someone would consider, so in theoretical computer science, this would be considered evidence for saying that sampling is hard, classically. So in this case of additive approximation, the first results were by Aronson and Arkhipov in Boson sampling. And then there were similar results from IQP circuits by Bremner, Montanaro, and Shepard. So before delving a bit deeper on these sampling problems, a small refresher of complexity theory. So probably most of you know these classes, which is P, the class of decision problems that can be decided in polynomial time. BPPs, the problems we can decide in polytime, and also with a polynomial number of bits, random bits. And then NP, the class of problems we can, of course, verify the proof in polynomial time. So then we have these classes, and contained in all of this, there's this so-called polynomial hierarchy that I mentioned before. So for those who don't know, what is this polynomial hierarchy? So to define this polynomial hierarchy, we start from this recursion. So here these arrows indicate inclusion, set inclusion. And then, so of course, this kind of diagram, we can write it down as a recursion in this complexity classes. So all the classes over here on the left are what are called sigmas. On the right are the p's, and the center the deltas. And then the polynomial hierarchy, we can define it as the union of all these sigma classes. Then this thing, it's going to be, we're going to say that it's divided into levels. So there's the first level, the second level, the third level. And then we're going to say that the polynomial hierarchy collapses to the ith level if the whole polynomial hierarchy is inside this sigma I. So this is what is, so this thing that I mentioned here is what is thought to be unlikely, that the polynomial hierarchy collapses to some level. So this, you can think of this as some kind of generalization of that NP is different from P. So of course, it's debatable if this is really unlikely, but well, you should complain to complexity theorists. Then we have another class, P to the sharp P. So what is this exactly? So sharp P is the set of functions. So notice it's a set of functions that count solutions to NP problems. And then P to the sharp P is just having oracle access to these functions from polytime machines. Now we can define complete problems here. So one complete problem is computing the permanent of a matrix with 0, 1 entry. So we know this is sharp P complete. And well, there are graph theoretical interpretations of this permanent, which is counting a number of perfect matchings in bipartite graphs. Now, the fact this class will see how it becomes relevant. Of course, those who know Boson sampling know that the permanent appears in the amplitudes of the output. And then, of course, we have BQP over here sitting awkwardly among all the other classes, just for reference. So okay, let's come back now to the sampling problem. So as I mentioned, Boson sampling was one of the first to be proposed. So essentially, we have some bosons, as we know, are described by some commutation relationships in their creation and destruction operators. And when to perform this Boson sampling, we just input some non-Gaussian states. So let's take this one over here, and we run it through a linear optics circuit. So linear optics in Boson case are just circuits that act linearly on the creation and destruction operators. And then we measure the output on the particle number basis, and one can calculate that the amplitudes depend actually on the permanent or on submatrices of the unitary that represents that is represented by the circuit. So that means that these the amplitudes or the probabilities are sharply hard to compute. Now, of course, it doesn't mean that they are hard to sample from. This by itself doesn't imply that, but it's one of their required ingredients to show it. So enough of bosons. What I want to show you is fermion sampling. So first, what are fermions? Well, they can be described very similarly to bosons. So any system of n fermions and d modes can just be described by like the antisymmetrized space of the d level system, and then you just take the tensor sum up to d. So of course you can just have one fermion per mode, and then you can define the creation and destruction operators as in the bosonic case, but now you impose anti-commutation relations. And alternatively, as a description, one could use what are called Majorana modes. Now we have these Majorana modes. So you have two per each mode in the system. And then with these operators, we can define what is called the Fock basis state. So we are taking some order in the creation and destruction operators here. And over these states, we can act in two different ways. So we can act on what is called passive Fermionic Linear Optics, which acts linearly on the creation and destruction operators. So this would be an analog of the bosonic case that I showed before. And these operators preserve the particle number and form a representation of the unitaries. Alternatively, we can act with what is called active Fermionic Linear Optics. So these are linear on the Majorana operators, and they only preserve parity. So these are operators, you can think them as unitaries generated by Hamiltonians that are quadratic in the Majorana operators. And they represent, they form a representation of the special orthogonal group. So, okay, we have these fermionic modes. There, if you haven't heard of fermions before, but you know qubits, then you can just translate between them using what is called the Jordan-Wigner transformation. So, for example, we can just take any Fock basis state over here, and that gets translated into a computational basis state. We can also take the Majorana operators, and they will be translated into these Pauli strings as well. We can, all the particle number measurements will translate into computational basis measurements, and any local particle preserving Hamiltonian, quadratic Hamiltonian gets translated to these operators over here. Now, why I'm showing this is just to say that you could easily, what I'm going to talk about, the Fermion sampling scheme, you could easily implement it in superconducting systems if you wanted to do it experimentally. It's not the only physical system that you could implement it, but it's at least one. And then, okay, so we have our fermions. How do we sample from them? Well, let's consider passive FLOs that preserve the particle number. And let's input the same state I mentioned before, this state from the Boson sampling case. Now here a first problem will appear, which is that the output amplitudes will not be permanents, but now will be determinants of matrices. And this is a problem because the determinants, you can compute them efficiently, in contrast to the permanent, which we saw was Sharpie complete. So all these results about hardness of sampling will not work in this case. We cannot just imitate what we did in the bosonic case. Also, if we did try this with active FLO, actually this active FLO are, you may know them as match gates, and there are many results that these circuits are classically simulable, and it's easy also to sample from probability distributions they generate, so it would not work either. So in our scheme, what we're saying is that instead of giving us input these basis states, we are going to input this what we call magic states, shown over here in the particle number basis, and here shown how to produce them as qubits using the Jordan-Wigner transformation. So essentially, we just input several of these quadruples, and then you sample as you would do in any other scheme. Now you can show that for the passive case, the probability outputs can be written as this square of sum over determinants. So now it's not the determinant, it's sum over determinants. And you can show that these things are actually Sharpie hard. This was actually done by Ivanov years ago. Moreover, for the active case, what we find is that you can actually write this as the sum over Fermions. So here I wrote M, not U, you can see, because this matrix, it's defined from U, so it contains entries of U, but it's not exactly U. But anyway, the point is that you also have a probability output that is sharply hard to compute, and now we have the required ingredient that we were missing. Also, I should mention that these things over here also have graph theoretical interpretations, just as the permanent or the determinant, these ones do also, although a bit more involved. So, okay, we have our probabilities. And then I should mention that when you have fermionic linear optics, you can do the same kind of decompositions you have in the bosonic case. That's not a problem, like these ones over here. And well, the kinds of gates that each of these two mode gates that you have, you can have them for the passive or the active case. And here I should remark that the kinds of gate you need to implement these are actually quite easy to implement in superconducting quantum computers. These root square of I swaps and I swaps are very easy to implement. So it seems quite good for that, yeah. Now, okay, so we have the scheme. And we have our circuits, we have the input states. Now, what do we show about this? Well, I'm going to show now 3 results. The first 2 are about the hardness guarantees. So it's about showing that, showing evidence that sampling from these things is hard. And this third result over here, the efficient certification of FLOs. So here I don't mean some kind of certification. I don't mean like cross entropy certification that they kind of Googled it, although it could apply to our case as well. I mean something much more simpler. That's why I put it between quotes here. The idea is that if we are given some FLO, then there's some, there's some scheme to give an estimate of this V. With a polynomial number of measurements and in polynomial time. So the idea is that we just input, the idea is quite simple actually, you just input these 2 kinds of states, so the plus state in the X basis, the plus state in the Y basis, and you just measure these polystrings. Now if you remember, these polystrings were the Majorana operators that I showed before, so yeah, you can reconstruct the gates quite easily. That's a nice thing about the structure of FLOs. But anyway, now the important are the hardness results. So why do we want these things over here? What does anticoncentration mean, or average gauge Sharpe hardness? Well, to understand that, we need to understand that hardness of computing probability outputs, like for example, that the permanent is hard to compute, Sharpe hard in the worst case, does not imply by itself that it's hard to sample from this probability, these output probabilities. So how do we connect those 2 things? Well, we have the statement that we have some machine that can efficiently sample from these distributions. And we want to conclude that the polynomial hierarchy collapses. So we're going to pass to this intermediate statement here that about that if we can sample, then we can relatively approximate the probabilities on average. So the first step for this is using the Stockmeyer's algorithm. So Stockmeyer's algorithm says that suppose you're given some Boolean function and you're given some output of this function, then there is some BPP machine that with Oracle access to NP and to the Boolean function will be able to give some, will output a number, this A, which is a multiplicative approximation of the probability P that the function outputs Y. So, okay, why do we want this algorithm? So the idea is that we are going to feed to the Stockmeyer algorithm as F, the efficient sampler, the classical efficient sampler. And then Stockmeyer will be able to give a relative approximation of the probability as it's stated here. Now, one thing to notice is that here I wrote on average, and Stockmeyer is just giving me an approximation of an output. So there's another ingredient missing here that I mentioned soon. And the second thing to notice is that this relative approximation is in the 3rd level of the polynomial hierarchy. Why? Because, well, it's known that this PPP to NP is inside the 3rd level of the polynomial hierarchy. So now things start connecting to the collapse. So the other ingredient I was going to mention is the anticoncentration. So anticoncentration tells us that what it's telling us is that the probabilities are not too small. The idea is that you try to, so the efficient sampler could be adversarial for the Stockmeyer algorithm. So you bypass this by using anti-concentration, by proving that the circuit's anti-concentrate. So, okay, that's the second ingredient. And then, okay, we need to prove that the polynomial hierarchy collapses. So these are the two things. The one is Toda's theorem, that the polynomial hierarchy is inside this class that I showed before. And then we use a conjecture. We conjecture that this relative approximation on average is it's Sharpe hard. So it's average case Sharpe hardness of approximating this probability. So this is conjecture. And then if this conjecture is true, then that means that P to the Sharpe is inside this class because of Stockmeyer's algorithm. And then the polynomial hierarchy must be inside the third level, and the polynomial hierarchy collapses. So, okay, that's the whole logic of it. Now, a few things to say here is that this conjecture is hard to prove in all of the sampling schemes. So what you instead prove is that it's average case hard to approximate the probabilities up to an error 2 to the minus poly n. So if this was actually proven for errors 2 to the minus n, then that would show the conjecture, but that's too hard for now. Second point is that this anti-concentration holds for random circuit sampling. It's known because they form a 2 design, so it's kind of easy. But it's not known for Boson sampling, actually. It has not been proven. Interestingly, now we're in the fermionic case, these circuits don't form 2 designs. So it was not obvious that anti-concentration would hold. In my opinion, the most interesting result of the paper is this, that these things actually anti-concentrate. So yeah, okay. So now we know what's the logic of this proof. Let's go deeper. So what's anti-concentration then? We saw it before. The idea that for a large fraction of the probability outputs, they are big enough. And then what's the idea for proving this? Well, the proof is kind of long, but I'll show a bit of the idea. So we use what's called the Paley-Sigmund inequality. It's shown here. And then we compute these moments over here, these expectation values. And we rely heavily on representation theory, actually, of these groups of the active and passive fellows. So the idea is that, okay, you take, so Paley-Sigmund, we can take the random variable as the probabilities, and you can take some reducible representation of the group, either unitaries or the special orthogonal. Now computing the expectation value it's easy, it's Schur's lemma if you know about it. So that gives us the first moment. And then the second moment is more involved here. There are some details, but essentially it boils down to the fact that this expectation value can be written in terms of the trace of a projection. That this projection is a subvector space of the tensor space of the 2 Hilbert spaces. So the point is that when you write it like this and you have an explicit expression from this projector, then it's easier to compute things. And if you replace these 2 things over there, then you can bound them. So you first bound these things over here, the dimension of these spaces, that's easy. And the second thing to bound is the trace over here. So this was like a large chunk of the paper, I guess, bounding this trace actually. But it turns out that it scales this in the same way as the quotient over here, so they cancel out. And then you have that this whole thing is a constant. Yeah, so that's the idea of the anti-concentration. And then, okay, let's let's move to average case hardness. So how do we prove the average case hardness? So there are techniques for this that were developed some years ago by the groups over here. Which one over here? Bulan, Pfefferman, Mirke, Vazirani, and Movasak. So the idea is that we're going to, what they did is that they take some circuit C, and we know that there are some worst case Sharpie hard circuits, meaning that the probability outputs are Sharpie hard. And so we are going to consider such circuit, and here the C1 to Cm are going to be the gates. And then this is how Movasak proceeds, which is he takes some random Hermitian operators, and then he considers this map, which is called the Cayley map. So this maps the real line to the unit circle in the complex plane. So if this was acting on Hermitian operators, not to a unitary actually. And then each gate on the circuit is perturbed by some parameter theta. So it's perturbed in this way. This gives rise to the whole circuit being perturbed by this theta. And then we can define a polynomial that depends, that it's actually the output probability of the circuit. Now this polynomial is going to be relevant for the average case hardness. So why? Well, we're going to use polynomial interpolation. So the idea is that this polynomial evaluated in 0 is our worst case circuit. So it's Sharpie hard. And then what we want is that we're going to evaluate several points on the polynomial. And if we know the value of them, at least approximately, then we can interpolate to the worst case. That means that if we can compute the probabilities for some fraction of the circuits, then it implies that we can compute it for the worst case, and it would imply the Sharpie hardness of the average case. So how to do this exactly is that first it is shown that for the distribution of the circuits for theta, when theta is not near 1, if you sample from those circuits, so in this band, you are actually sampling close to the hard random distribution. And then using polynomial interpolation technique, here, if you know about these things, there's the Paturi lemma, etc. You know that then you can prove that if you sample enough points and you have a fraction of them computed correctly, then you can interpolate to the worst case. And then you have reducing the average, the worst case to the average case. So that's the general idea. Now for our case, we use this technique very similarly to them. Just a small change, we need to generalize for the active case because we are not working with the same group in the case of the active FLO. So for example, here we have the Lie algebra, the Lie group, and the Cayley map here written as acting over operators. If you have some path over the Lie algebra, this generates a path on the Lie group. And now in the case of Movassar, when he does this, as I showed before, it's perturbing each gate individually, which perturbs the whole circuit. Instead of that, what we are doing is perturbing the whole group operator, so at the level of the group, which in the language of the circuit, of the representation of circuits, is perturbing the whole circuit altogether. So this actually allows us to generalize this thing to the special orthogonal group and any of these these compact Lie groups. So it's some small nice generalization. And using this, then we could show that it is sharply hard to approximate these probabilities to this exponential error, so exponential of minus n to the 6, with some big enough probability. So actually, well, so Movasag also does this, and he obtains this result in the case of the Google layout that Google uses. He gets 4.5. Okay, it's better, but we can live with that. And actually, as I mentioned before, to prove this conjecture, we would be required, or any scheme actually would be required to show this up to exponential of -n. This is, of course, open, but there are some more recent results. This came after we put the paper on the archive, where and so these results, they actually can be applied to our scheme as well. Give an error which is exponential of -n log n. This is for constant depth circuits, and well, this is here is the result for more general result, which depends on the number of gates. So this is quite amazing, I think. Like, it's only a log factor away from proving the conjecture. I mean, that's amazing. Of course, now to prove this, the techniques they still use these polynomial interpolation techniques. They just modifies some things in the proof. But the point, so especially this paper, what it shows is that we kind of need some other different technique altogether to get rid of this logarithmic factor. So yeah. So okay. So what I have shown you so far is this. We showed the anti-concentration, the average case hardness, efficient certification. Also, I showed you that it's experimentally feasible. So yeah, I think it makes up for a nice scheme. And now let's talk a bit about what open problems and some thoughts about this scheme. So one thing is there anti-concentration at lower depths? So so there's some paper about random quantum circuits where they talk about that the circuits anti-concentrate in log depth. Actually, this plot over here is some like preliminary simulations we had where it's, so the idea, so number of quadruples here is the psi force that I showed before. This magic states is the number of magic states, and then we check for the minimum depth that is required, so that this is the constant that appears in the Paley-Sigmund inequality, is the minimum depth for this thing over here to surpass some threshold. And it seems that we don't require much depth to pass those thresholds, which is kind of suggesting that these circuits might also anti-concentrate in log depth. Second thing, well, this is more like, it says applications. I'm not sure how much of an application really is, but so it's known that Gaussian boson samplers have some applications for graph theory. This is related to the matchings that I was mentioning before. All these probability outputs, like the sum over determinants, sum over Hafnians, have interpretations related to matchings, colorings, etc. So maybe there's something for fermions also, some kind of analog, especially considering that active FLOs are an analog of Gaussian boson samplers. Third is there's some relation to chemistry problems. So this is a paper from Google where they do some hard tree fog simulations, and well, if you see the kind of gates they use, they're very similar. And of course, all these things are fermions. So one could think, okay, is there some kind of chemistry sampling problem where maybe these guarantees might apply? That I don't know, but that would be quite interesting as well. And finally, this paper was shown to me a little while ago. And it was interesting. So here in this paper, they study bosonic systems, and using these results of sampling complexity, they study there are phases where it's easy to sample, hard to sample from, and there should be, of course, a change in the physical behavior of the system, and this, of course, they're calling a dynamical phase transition. And then, okay, is there some interesting thing to say about phase transitions in fermionic systems? Maybe, I don't know, but that's something I'm curious about as well. So anyway, I think I'm done. Yes. So thank you for your attention, and in these COVID times, please be a fermion and stay safe.
Okay, thank you. Thank you, Mauro. That was awesome. So clap, 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 clap. I see Robin's clapping too on the chat. So does anyone have any questions I'd like to ask Mauro?
Yes.
So did someone say something? There's a noise dropped out.
Hi, Mauro. Yeah, maybe I'll start. Can you say a bit more about why you choose the initial state, this phi, like the initial state that you use called magic state?
Yeah.
Is there any intuition or what reason?
So the reason why we applied in this paper is because of this paper of Ivanov, actually. This is why. But actually we could have, okay. So we would not have needed to actually use this state, because in the paper I showed at the beginning, here, this one, they actually show that there are like sort of families of magic states, of fermionic magic states, that you can choose so that the output probabilities are sharply hard. Now, why does this, okay, why does this state in particular, for example, give this thing? It's because the tensor product, if you see, is going to give you like all the binary strings. So if you take psi4 and you take the tensor product, it's going to give you states that look like all the binary strings, such that the ones and the zeros are paired up. Okay, and that you can, it's kind of, if you act with the unitary over it, it's going to take like submatrices that look like this thing over here, the determinants of those things. But yeah, we didn't need to actually take this one in particular. It would have been any other equivalent state. And with equivalent, I mean this state with some UFLO, with active FLO acting over it. It would have worked anyway, of course. So yeah, I don't know if that answers the question.
Okay. Another question is, in your proof, I think like you said, that's the most technical part. There's a ratio that cancels out.
Yeah, the anticoncentration. Here.
Right. So you said it's big O, but like they are dividing each other, right? So is it theta or one of them is omega? I don't know. You cannot prove anything.
Yeah. That's right. Yeah. That's yeah. You're right. This one should be omega, right? The one over. Yeah, that's right. This is a type. But the point is, yeah, they're right. But they end up canceling when this is omega, right? Yeah.
Okay, thank you.
Thanks by that. By the way, I should correct it.
So are there any more questions? I have one if no one else does.
Mm-hmm.
One of the questions was around the improvements to this result in the average case hardness. So you mentioned, for example, that there's those papers from early this year, right? Yeah, those final. Is it hard to apply that general result to the fermion case, or is it just fairly straightforward?
No, it's fairly straightforward, I would say. I mean, it's not hard at all. They just modified, so they just modify actually this Paturi lemma. So when you do the when they do the interpolation, they use something called Paturi lemma, which tells you that if I take this, if I compute these points with some error, I still can compute the thing over here with some error. And they just modified that part of the proof. So it wouldn't really, it would still apply. Makes sense?
Oh yeah, that makes sense. Are there any further questions?
Yes, I'd like to ask a question about experimental implementation. I was wondering how many qubits would you need, and whether it's more difficult. I would assume it's more difficult because photons are way easier to manipulate than superconducting qubits.
Yeah.
Yeah. So what do you think about that?
Okay. Well, I'm not an experimentalist, but yeah. So what we've seen, probably, I don't want to say something wrong here. Of course, if you implement this in superconducting qubits, I would think it's easier than photons, but I might be wrong on that. And about the number of qubits you would need, the problem is that actually I was going to put it on the open problems. What are we need to know what classical algorithms we have that can simulate these systems, right? So that, so to know what would happen in the case that, for example, Google ran this and then IBM at the other day said, hey, we can simulate this with this number of hours. So probably the numbers would be similar to random circuit sampling. To say, okay, we have some advantage and your supercomputer is going to take, I don't know, 1 full year to simulate this or whatever, but we don't really know that much yet about simulating these circuits. There's not a lot of work on that. It's actually something we want to explore. How efficiently can we simulate the circuits to know in an experiment how many qubits would be required, or modes in this case. So the short answer is that we don't know.
Awesome. Okay, thanks.
Yeah.
So for the implementations, do you have any, I guess you are suggesting it will be implemented using qubits, like superconducting architecture.
Yeah.
Right, okay.
Well, yeah.
Not like boson sampling have very natural media that you can use.
Yeah, the thing is that it's very hard to have actual fermions be non-interacting, right? Because if you have like electrons, they are going to interact. And so yeah, it's
can I think of the result as you have a family of circuits, but if you choose some input states, it's trivial to simulate. Then the solution is then you choose some other input states, even though that the circuit may like relate to fermions, and it's easy to simulate. But when the input states as sort of magic states, you recover the hardness. Yeah,
but this is the same as boson, by the way. So boson, the input state that you give to boson sampling, this is not Gaussian.
Mm-hmm.
So it's the same logic as boson sampling. Okay. The input we are giving is non-Gaussian as well. So what I mean with non-Gaussian is it's not produced from some FLO acting over a basis, over a Fock basis state.
Okay.
So yeah. So well, in the Fermion case, right? So yeah.
Yeah.
So yeah. What you said.
So I wonder whether like there's more general scheme that you can consider, like like Fermion sampling is of course a very good name and generalization of boson sampling, but maybe there's something more general. It's just
maybe, yeah.
Yeah, it's not anything that we know yet, but it's some easy to sample circuit with non-trivial input state, and yeah, the state may not correspond to any.
Right. Yeah.
Terms.
There's also results with the Clifford circuits as well, by the way. Like you have Cliffords easy to simulate, but then with some states it becomes hard.
Right.
Yeah.
Okay. Good, thank you.
I was going to say on that point, if you don't mind me saying something about that, Mauro, it's an interesting case because if you look at like the graph generalizations of all these problems, at the graph-based generalizations of all these problems for boson sampling, fermion sampling, Clifford circuit sampling, and random circuit sampling, if the goal is to generate circuits from something that has a local structure defined by a graph, then there's only a few choices that you can make that would make the circuit easy to simulate. So one of them is the match gate circuits, right? Which is kind of what's linked to the fermion sampling. And in the case of Clifford circuits, it's also clear. There's the Clifford circuits, right? But interestingly, that they're the only examples in finite dimension that actually have that property, if you're going to generate it like that. So it could be that this is it. And that's an interesting question. I mean, you could define circuits in a more complicated way where you don't build them up from like local graphical structures, things that can be related to a local graphical structure.
Yeah.
Yeah, it's interesting. These seems to be the only two cases. And they have very similar properties, both of them. Anyway, that's an aside. So if there aren't any further questions, or if there are any further questions, maybe chat them out now, but if not, we might wind this up. Okay, so if we have no further questions, we might thank Mauro one more time. Thanks, Mauro. It was a fantastic presentation.